Welcome. Today we'll discuss about vapor power cycle. A power cycle is a thermodynamic cycle consists of some thermodynamic processes that converts heat into mechanical work. We have already discussed about gas power cycle like Otto cycle, diesel cycle, dual cycle, etc. And in these cycles, gas power cycles, the working fluid is gas throughout the cycle. But in vapor power cycle, the working fluid converts its phase from liquid to vapor and again from vapor to liquid. And that is why this type of cycle is called vapor power cycle. Basically, vapor power cycle is also a heat engine cycle where the working fluid is vapor and liquid alternately. So there are many vapor power cycles including Carnot cycle, but Carnot cycle is not a practical cycle, so we will not discuss Carnot cycle in this video. We shall discuss the Rankine cycle and also the modified Rankine cycle in our next video. So a Rankine cycle is the standard operating cycle of any thermal power plant. In a thermal power plant, liquid like water is used and which is converted to vapor by a device called boiler. And again the vapor is converted to liquid by a device called condenser. There are also other devices in a thermal power plant that we'll discuss within a very short time. So as I have mentioned, the operating fluid is continuously evaporated and condensed. The evaporation is done by a boiler, steam boiler, and condensation is done by a steam condenser. As we know, water is most widely used operating fluid. That is why water is used in all thermal power plant, and the steam is produced and that steam is used to run the turbine, and also steam engine can be run with the help of this high pressure, high temperature steam. So Rankine cycle is the operating cycle for any thermal power plant. So let us understand the components of the thermal power plant first. So a thermal power plant must have a steam boiler which produces high pressure, high temperature steam from the water by application of some heat by burning some fuel, and the boiler has to be supplied the water continuously with the help of a pump. The steam that is produced at high pressure and high temperature is sent to the turbine or prime mover, where the steam is expanded in the turbine and we get some work output from the turbine. Steam engine is not used nowadays in any part of the world, so we will only consider the turbine as a prime mover. So due to the expansion of the high pressure, high temperature steam inside the turbine, the exhaust steam is low pressure, low temperature steam. This is actually a mixture of liquid and vapor. And this liquid mixture vapor is condensed in a condenser. A condenser is a device which converts the vapor phase of the working fluid to the liquid phase or steam to the water. So there must be one cooling arrangement in which some cooling fluid like cooling water is passed through this coil and the heat is extracted from the steam and cooling water become hot. And as a result of this heat exchange, the low pressure, low temperature steam is converted to water, which we call the condensate. Now this condensate or water is sent to the boiler, which is also called the feed water. And this feed water is pumped to the boiler because the boiler pressure is very high. So we need one pump which is called the feed pump, which supplies the water at high pressure to the boiler, and this way the cycle is completed. And in a pump we need to do some work to run the pump that we will call the work input to the system WP. And in a condenser there are rejection of heat. Due to this rejection of heat, the steam become water. So this is the complete cycle of a thermal power plant. Let us start from state 1. Said before pumping, the state is 1. After pumping at high pressure, it become state 2. After production of steam, it becomes state 3. And after expansion of the steam inside the turbine, the state of the working fluid is 4. So this 1, 2, 3, 4, there are 4 processes that constitute the Rankine cycle. Now let us draw a PV diagram for this thermal power plant. I think you are already familiar with this line, which is called a saturation line. And this is the critical point. This part of the line is called dry saturated line. That means this is the X equal to 1 for dry steam. So this line represents the dry saturated steam. And this part of the line represents saturated water. That means water at boiling point. And in this case, the dryness fraction is 0, but at saturation temperature. Towards the left side of the saturation line, this is the subcooled region, and towards the right side of the dry saturated line, this is the region for superheated steam. And this region between these two lines, this is the region for liquid and vapor. So this left side represents 100% water at saturation temperature, and the right side line represents the 100% steam, that means dry steam with no water particles in suspension. Now process 1, 2 is the pumping process. So point 1 is at low pressure and low temperature, and this low pressure, low temperature water coming out is pumped to the boiler, and because of the pumping, the pressure increases from point 1 to 2. So this is the pumping process 1, 2, and this is low pressure, say P1, and this is the high pressure, which is also called the boiler pressure, P2, and P1 is the lowest pressure. It is also the condenser pressure. So process 1, 2 is pumping process, during which work done during the process is WP. This is work input to the system. Now look at process 2, 3 in the block diagram. 2, 3 is heat supplied at constant high pressure. So 2, 3 represents heat supplies at constant pressure, boiler pressure PC. So this is isobaric heat supply. 2, 3 is isobaric heat added, and 3, 4 is expansion inside the turbine. So 3, 4 represents expansion inside the turbine, and during this process W out, that means work output of the turbine, is W out. So this point 4 is the low pressure point, and this represents the liquid vapor mixer at low pressure and low temperature. Then comes the condenser, that means the process 4.1. So process 4.1 represents the condensation, during which the system rejects heat to the cooling water, and say this is QR. And because of this heat rejection process, the liquid vapor mixer at point 4 is converted to saturated liquid at point 1, that means 100% water at point 1. Now we will draw the temperature entropy diagram for the Rankine cycle or this thermal power plant. This is the same saturation line for TS diagram. During the process 1, 2, the pressure increases from P1 to P2, and there will be slight increase in temperature from TS1 to T2. Now TS1 is the saturation temperature of water at low pressure. Now the next process is 2, 3. We can divide this heat addition process in 3 steps for our understanding only. Say from point 2 to A, this is the increase from T2 to the saturation temperature TS2 at high pressure. So after that, there will be no increase in temperature and there will be the absorption of latent heat of vaporization. So from A to B, this part represents latent heat of vaporization, and at point A, this is 100% water at saturation temperature. At point B, this is 100% dry steam at saturation temperature. And after that, there will be addition of superheat, and that will make the steam superheated steam. And this point 3 represents the temperature of the superheated steam, that is T sup. So this is heat addition from point 2 to 3 inside the boiler. This high pressure, high temperature steam enters into the turbine, and there will be expansion of the steam isentropically, and temperature decreases from T sup to this point. So since this is isentropic expansion, entropy will remain same because this is isoentropy expansion process, S3 equal to S4, and this work output is derived from this expansion process. Now look at point 4. Point 4 is in the liquid vapor mixer region. So at point 4, that means the exhaust steam from the turbine is liquid vapor mixer, or we can say wet steam. Now this wet steam enters inside the condenser and it rejects the heat to the cooling water, and because of the rejection of the heat, vapor will be converted to liquid. Ultimately we will get saturated water at point 1. So point 1 is heat rejection process, and the condensation takes place due to the rejection of heat, and finally we get saturated water at low pressure, and this is again pumped to the boiler and the cycle repeats. So process 1-2 is isentropic process. That means the pressure increases due to the pumping, and this is S1 is equal to S2. This is also isentropic process. Process 2-3 is constant pressure heat addition inside the boiler, so we'll call it isobaric heat addition. Now process 3-4 is expansion process, which is isentropic expansion from high pressure P2 to low pressure P1. Process 4-1 is isobaric heat rejection. So this way we can represent the 4 processes of a thermal power plant, and this is TS diagram for the Rankine cycle. Now we'll draw enthalpy entropy diagram, which is also called the Mollier chart. We have learned in the previous videos. In Mollier chart also, this is the saturation line, and in Mollier charts there are many constant pressure lines. We consider this, say, low pressure condenser pressure P1 and the boiler pressure P2. There are actually many constant pressure lines like these, but we'll only consider these 2 lines because we are concerned with this high pressure or boiler pressure P2 and the condenser pressure P1. So during the process 1-2, there is increase in pressure from P1 to P2, and that takes place isentropically. So 1-2 is isentropic pump work is done during this process. And from 2 to 3, this is constant pressure lines. So 2 to 3, there will be addition of heat to the system at constant pressure. So this is 3, 4. So this is QS. This is WP, pump work done on the system. 3-4 is isentropic expansion, work output of the turbine. And 4-1 is in the condenser, which is heat rejection at constant low pressure. Heat is supplied at high pressure, constant high pressure. Heat is rejected at constant low pressure, which is condenser pressure. And work is done by the system during the expansion process inside the turbine, and work is done on the system during the pumping process, WP. Now, analysis of the Rankine cycle. So first we'll find out the heat supply during the cycle, which is done inside the boiler, and during the process 2-3. So QS heat supplied equal to Q23, and from HS diagram for point 2 the enthalpy is H2, and for point 3 enthalpy is H3. That means H3 is the enthalpy of the superheated steam and H2 is the enthalpy of the water entering inside the boiler. So QS is equal to H3 minus H2. We can get the value of H3 and H2 directly from the Mollier chart. Now otherwise we can calculate the value of H3 from steam table. Look at the TS diagram. Corresponding to the point 3, this temperature is T soup, and point 2, this temperature is TS2, saturation temperature of steam or water, and this temperature is T2, and heat is added from point 2 to point 3. So H3 is equal to, at this point for the dry steam, the enthalpy is Hg2 corresponding to the pressure 2. That means this 2 is for pressure P2. Hg2 plus amount of superheat, that is equal to Cp soup, specific heat of superheated steam at constant pressure, multiplied by temperature of superheated steam minus temperature of saturation temperature of dry steam, that is Ts2. So from this formula we can get the value of H3, and we can get Hg2 from steam table and also Ts2 from the steam table. H2 is equal to, we can see the condition of fluid at point 2 is liquid. This is in the subcooled region in this TS diagram or in this HS diagram. So H is equal to CPW, specific heat of water at constant pressure, multiplied by the temperature is T2 here. So this is T2 minus T naught, which is 0 degree centigrade or 273 Kelvin. So if we take this, then this will be CPW into T2. So this way we can calculate the amount of heat supplied during the process 2-3. The formula will be different if the steam produced by the boiler is dry steam or if the steam produced by that boiler is wet steam. Now the work done by the turbine or the steam engine W out, and work is done during the process 3-4. So we can also say W34 work done during the process. From the HH diagram you can see this is equal to the enthalpy drop due to the expansion process, and that is equal to the change in enthalpy from H3 to H4 during the process 3-4. In this case also we can use the Mollier chart and get the values of H3 and H4 directly from the chart. Otherwise, and H3 is equal to, already we have shown how we can calculate H3 for superheated steam. Now the H4. Now what is H4? Look at the TS diagram. The condition of steam at point 4 is wet steam. Suppose at point 4 the dryness fraction of the steam is X4. For this the saturation temperature is Ts1. Already you have mentioned low pressure. So what will be the value of H4? That means enthalpy of the wet steam, that is equal to HF4. 4 is for the point 4 plus the dryness fraction is X4 multiplied by latent heat of vaporization HFC for 4. So to calculate H4 we will have to use the steam table corresponding to the condenser pressure P1 and the saturation temperature Ts1. Now we will calculate the pump work WP during the process 1-2. From enthalpy entropy diagram we can say WP is equal to H2 minus H1. and for that we have to calculate the value of H2, enthalpy at point 2 and enthalpy at point 1. For enthalpy at point 1, it will be with respect to the pressure P1 and temperature TS1, and it is HF, that means sensible heat, because it is saturated liquid or saturated water. And for H2, we have already mentioned how to calculate H2. Now there is another way to calculate the pump work, and that is for the flow work. Process 1, 2 is a flow process, so work done on the pump is equal to volume, specific volume multiplied by change in pressure dP. So in this case you can see the PV diagram here. From point 1 to 2, this is the pumping process, and due to which the pressure increases from P1 to P2, and there is no appreciable change in volume during this process because water is incompressible. So we can say volume V1 equal to V2. And what is volume V1? From PV diagram or TS diagram or even HS diagram, this volume V1 is equal to the specific volume of water at pressure P1. So this we can get from the steam table. So volume is Vf1, that means pressure P1 or 4.1, and change in pressure is from P2 minus P1, that means pressure increases from P1 to P2. From this we can calculate the value of pump work. Now the efficiency of the Rankine cycle, eta Rankine, is equal to, this is W net work done during the cycle and heat supplied to the cycle. So W net is equal to W out, work output of the turbine, minus WP divided by QS. H3 minus H4 minus VF1 P2 minus P1 divided by QS, that is equal to H3 minus H2, heat supplied during the process 2-3. Now if we neglect this pump work, this can be neglected, this is very small compared to. So if we neglect the pump work, then the Rankine efficiency is equal to work output is the turbine work itself, that is equal to H3 minus H4, the enthalpy drop in the turbine, divided by heat supplied, the enthalpy gain during the process 2-3. And this is the formula without pump work. The only thing is how to calculate H3. So value of H3 depends on the condition of the steam produced by the boiler. So in this case we have shown that H3 is superheated steam, but it may be dry steam also. Then if the point is this point, then it will be like this. So in that case the value of H3 we can directly get from steam table, that is the value of Hg, enthalpy of dry saturated steam, from steam table. And this may also be wet steam. If it is wet steam, the point 3 will be over here and this will be point 4. Value of H3 has to be calculated like this, HF plus X into HFG. And in the next video we'll discuss about modified Rankine cycle. Thank you.